you notice that we ended up focusing on the X and Y submatrix, that block, because this third row was a special row, right? It didn't have very much going on. It had zeros everywhere except for in one position, in one spot, right? This one right there. That's the only place that there was not a zero in that row. And so for that reason, all of those zeros end up telling us that we can focus just on this 2 by 2 block right here in order to compute the determinant of my matrix. And so the generalization of that is what we find here in this fact number 524. That if I have any row, or indeed any column, it also works for columns, that contains all zeros except for a 1 on the main diagonal. So the diagonal is just the upper left to lower right, the place where the row number and column number agree with one another. So it's the diagonal entries, the first row, first column, second row, second column, third row, third column, and so on and so forth. So if I have a row that contains only zeros except for a 1 on that main diagonal, then, and here's the cool fact, we can just get rid of that whole row and that whole column, even if the column happens to have some other non-zero stuff in it. We can get rid of the whole row and the whole column and get a smaller determinant whose value is the same as the determinant that came before it. And the same is true for any column that has all zeros except for a 1 on the main diagonal. Now that we have a dimension reduction strategy, we want to get a little bit of practice using it in increasingly more interesting situations. So the first of these activities, activity number 5, is going to have you just take this 3 by 3 matrix and strip away a row and a column and find a 2 by 2 matrix whose determinant is the same as this original matrix. And then do some things that are a little bit more subtle, that are going to make use of what we learned in our previous class about how row operations can be used to help simplify a determinant. So the basic bag of tricks is this. If I have a matrix and I want to rewrite it as a matrix whose determinant is easier without changing its size, without changing the dimension of my matrix, then I'll be using elementary row operations to do that. If I want to rewrite my matrix as a simpler determinant of a smaller size, that's when I'm going to use this strip away a row and a column idea. And so we can use those strategies together. We can use elementary row operations to give us one of these magic columns or magic rows that is 0 everywhere except for a 1 on the diagonal. And once we have one of those magic rows or magic columns that's 0 everywhere except for a 1 on the diagonal, then I can pull out that whole column and pull out that whole row from the matrix, and I have a smaller determinant with the same value as the determinant that we just had. So let's get a little bit of practice doing that by working on activities 5, 6, and 7. So now you've had a little bit of practice with what dimension reduction actually looks like for taking 3 by 3 determinants, for example. So if I have a matrix that is already sort of miraculously set up with one of these magic rows or columns that has a 1 on the diagonal and a 0 everywhere else, then all I have to do is just pull that row and that column, right? You get to pull both of them out, both the row that has the 1, 0, 0 or whatever, and also the same column as that 1 resides on. Pull them both out, and then you get a smaller square matrix whose determinant is equal to the original. And so in this first example, we recognize that the first row of this matrix is one of those magic rows. And so I can take the whole first row and also first column out of this matrix and get a 2 by 2 matrix whose determinant is going to be the same as the original. And so one of the things that we sort of need in this process is, it would be nice at least, to have a way to find the determinant of a 2 by 2 matrix without having to continue to do row operations on it. And so for that, we have kind of a nice, this is one that we just sort of give you for free at some point, that if I have a 2 by 2 matrix, A, B, C, D, that using the linearity of the determinant, I can factor out an A from the first row and then a B also from the first row, and write the first row as a linear combination of 1, 0 and 0, 1, and then do the same thing for the second and third rows, and then use this principle to figure out that the determinant of a 2 by 2 square matrix, and I don't remember if we said this last week or not, but now is as good a time as any. The determinant of a 2 by 2 square matrix is the product of the entries on the diagonal, A times D, minus the product of the entries on the anti-diagonal, B times C. So usually when in my sort of mental picture, when I'm finding a determinant of a 2 by 2, I'm just kind of drawing this little half of a bow tie here, A times D minus B times C. And then that gives me the determinant of a 2 by 2. So that's the one shortcut that I will say it's okay to use in the process of sort of learning how determinants work and how to compute them. That's the one shortcut that's going to be okay. There is that 3 by 3 shortcut that was mentioned in the chat a little bit ago called Sarris's rule, or the Sarris method, which can find determinants of 3 by 3s by writing another copy of the 3 by 3 matrix next to the original and then multiplying out along diagonals. So in case anyone is interested in that method, just get a picture of that up here on the screen real quick. If I want the determinant of a 3 by 3, I write that matrix twice, and then I draw 3 diagonal lines going down and to the right, 3 diagonal lines going up and to the left, and I add the 3 that I drew in the beginning, and I subtract the 3 that I drew at the end. So this is a sort of quick and dirty, I call it a parlor trick to find a 3 by 3 determinant. But again, because what we're trying to do is develop theory in our course, this is a nice trick if you're in a physics class or something and you need a 3 by 3 determinant on the spot. But for our purposes, I want you to avoid this kind of shortcut. The one kind of shortcut I can endorse is the 2 by 2 shortcut, because there's not much of a reason to repeat this 2 by 2 calculation all in its gory detail every single time.